number that we're going to talk about is the number, it's E, is how we represent the number. It's called Euler's number. So you guys already know kind of the famous number. You guys know the number pi. Right? Pi is an irrational number. It goes on forever. And it's a famous number for various reasons. Right? It has to do with circumference. It helps you with circles, stuff like that. There's another famous number. That famous number is called Euler's number because Euler is the guy who discovered it. Euler in here? Yeah, there it is. So Euler discovered this number and they named it after him. So they represent it with the letter E. It's just like in the sense that it's an irrational number that goes on forever. So the question was like, how do you discover a number? You're not really discovering the number, like he didn't invent it, but he discovered a trend in something, and it has to do with exponential graphs. It has to do with stuff that's a little bit beyond our reach, but that's what Euler's number does. So we're going to look at some graphs, so later on in the unit, it might help a little bit to see what it is. But at the end of the day, all you really need to know is the letter E represents a number that's irrational, goes forever. This is a rough estimation of what it is, so 2.718. You don't need to know those numbers, you really don't. Euler's number is in your calculator. So if you look at your calculator, it should be the division symbol. So if you look at the division symbol, you should see this little E above it. If you went second and then the division symbol, that would bring up E. And if you hit enter, it would just tell you what the number is. 2.718281, 828, and then they know what should be here. We use Euler's number in this unit. We use it with logs. So we learned yesterday about what a log is, and before we actually do it, we're going to talk about it again. So a log, there's always some number here, here. And we say that there's different parts of this thing. So we call, when it's number 3 here, we call that the base. This number 4, we call that the argument. And number 5 over here, we call that the value. That's just the terminology we use. So the way Euler's number gets used in logs is they use it as the base number. So you'll see log base E. And that's how they use Euler's number. They call that the natural log. Instead of actually writing it out as log base E, they write it out a different way. So for instance, we're going to try to calculate this right here. So we're going to calculate log base E of 5. So remember in your calculator, you go log 5 divided by log E. And if you hit enter on that, so you go log 5 divided by, remember to close your brackets, log E. Your answer would be 1.609443. What's this special? It's the division symbol. So go second in the division symbol. There's another way to write the word log, and it's the ln. So if you look on your calculator, it should be right below log. Maybe see that? So it's just ln. So you just need to calculate ln5, you go ln5, enter. You're going to notice it's the exact same thing. The reason why it's the exact same thing, when you see ln, they call that the natural log. That means it's log with a base E. So they've written it right here for you. ln equals log base E. The same thing. Sometimes natural logs throw people off like really bad for some reason. That's all you really need to know about them. Natural logs is just a quicker way to write out a log that has a base of E. So instead of writing out the whole thing, you just go ln. And everybody in the room should just know that means log base E. If you're really confused on it, you can always just change it to log base E if you wanted. I mean, it would give you the same answer, but it's a lot easier to just in your calculator hit ln instead of having to go to log base E all the time. The rules for natural logs are the exact same as rules for regular logs. So what we're going to do is we're going to practice converting some equations here. These are exponential equations. We want to create logarithmic equations. So if I wanted to change this to a log, I would change it to be log. E would become the base. 2 would become the argument. X would become the value. So remember, that's how we get exponents isolated by themselves. I would not write it this way, because I would not write log base E. Instead, I would write ln of 2 equals x. These both mean the same thing, but the bottom one is how I write it, because that's quicker than writing log base E. Alright, so just like yesterday, we can solve equations that have exponents that are unknown. To do that, we change it into log form. So if I want to convert this thing, I'd convert it to be the natural log of 3 equals x plus 1. Instead of writing log base E, I'm just writing ln for natural log. I can calculate these values. So if I want to figure out what x is, I minus 1 from both sides. I go ln of 3 minus 1 equals x. My calculator, I go ln of 3 minus 1 and 0.099 equals x. Do you close the bracket? Definitely. So in your calculator, you need to go log, and then it has a little bracket, and then 3, and then bracket. So your argument should be in brackets in your calculator. If you don't do that, I think it does throw it off. Which I know it will throw it off. So make sure you're closing the bracket on your argument. Great. We look at C. We can do it again. We can't change that into log form right now. The reason we can't change it into log form is we don't have the exponential function by itself. So I need to subtract 2 from both sides. So I have e to the power 2x equals 6. Now that's an exponential equation. Now I can convert it into a logarithmic equation. Then it changes to ln of 6 equals 2x. To calculate what x actually is, I'm going to divide both sides by 2. So if I went the natural log of 6, ln 6, and divided by 2, I have 0.896 equals x. And you can round that to whatever you want, because it didn't say what to round it to. So I'm just doing the nearest thousandth, but on a real test it would tell you. All right, go ahead, see if you can solve the exponents of all those things, and try to use natural logs to do so. The last one's definitely the hardest one, and give it a shot. The first one is pretty basic. So you've got e to the power 2y equals 1. You can change that into log form right away because it's already got the power isolated by itself. Now, I could have solved that without changing it into log form. How could have I solved that just by looking at it in my head, knowing that y was going to equal 0?
Anything to the power of 0 equals 1.
There you go. Anything to the power of 0 equals 1. So if I have a power equals 1, then the exponent must equal 0, unless the base was 1. And again, that's possible, but the base was e. So the only way e to the power of something was going to equal 1 is if that something equaled 0. So you could have looked at it and observed it. That'd be pretty tricky to catch on to, but it's possible. Yeah.
So if I was on our diploma or something, and it was what is the value of y? But if we looked at it, if it's already equals 1, we wouldn't even have to do the question.
Wouldn't even have to do it. You could just know this exponent has to equal 0 somehow, y equals 0, because that's what would make it 0. Yeah. The second one, you definitely do have to convert that one. So you change it into an exponent or to a log form. I use the natural log. I call it ln. So instead of calling it a log. So I change this into ln 2.5 equals, and then the exponent is now by itself. I need to move the 3 over, then divide by 3. Remember, there's some invisible brackets here, so you need to calculate the top before you divide by 3. And that can throw you off on your calculator. So make sure you calculate the numerator before you divide by the denominator. And the last one has to do with getting the power by itself. So you can't change things in the log form until the power has been isolated. So I needed to move my 4 over and then divide by 2. Then I had a power by itself. And at that point, I can change it in the log form and calculate what x is. That's mainly a review from yesterday. It's just using a different base. Yeah. Like the 2 to the e and then the 2x plus 1. You only do that if the 2 is also an exponent. So that would be if it was like right here, then you distribute it. But it's on the outside like that, so you just divide it. Yeah, it's a coefficient. Alright. Convert these logs into exponential form. So you're going to notice that these logs are natural logs, so they're logs. So converting them, you don't know what the base is unless you remember what a natural log is. So if I wanted to convert this thing, I need to know what the base is. And then a natural log, the base is e. So e to the power of 2 equals x. And I could actually calculate that. So my calculator, if I went e to the power of 2, that makes 7.389 equals x. So changing these things is the exact same as yesterday. It's just now the base is always going to be e, because they're all natural logs. To do this one, we can't convert it into exponential form until we have the log by itself. Once the log is by itself, we can change it into exponential form. And then we can actually calculate it.
So with whatever it equals,
yeah, whatever it equals becomes the exponent. So this turns into the exponent, the base stays as the base, and then the argument becomes the value. A little bit easier.
So it's ln.
Yeah, so ln means there's a base of an e. So we didn't know what the base was because they didn't have to write it because it's natural log. That's the tricky part with this one, because before we could just see what the base was, right? It was kind of easy. Without the base being written, it's a lot harder. We'll do this again, but remember, you want to get the natural log by itself before you convert it. So we're going to subtract 1 from both sides. So I have 3 natural log x equals 9. And then we divide both sides by 3. We get the natural log of x equals 3. Natural log of x equals 3, same as this question right here. So you could actually just isolate it from it, but let's convert it again. So, so when you have a natural log, the base is base e. You write it in an exponent. So you change it from log form to exponential form, because then whatever your argument was would be isolated. So go ahead, try to solve the next 3 on your own. I'll write my answer below. The first one converts nicely. As long as you remember that logs have a base of e, it's a pretty quick transition. The second one, we had to divide by 2 first to get the natural log by itself. And it became e to the 11 equals 7. The last one, I had to move my 6 over, so I added 6 to both sides. Then I had to divide by 2. That got me my natural log all by itself. I then had to change it into exponential form because I was trying to figure out what the argument equaled. And it turned out that x equaled 20.1. Alright, that stuff with natural logs really shouldn't be that challenging. It's just understand the idea that natural logs are base e. And you write it as ln instead of writing it as log. The more challenging part of today, stretching your question. Yeah, it should, because it's just like basically review, right? So you're getting it twice now. Today, what we're going to do is we're going to learn 2 log laws. There's 6 log laws in total that we're going to learn. 6, maybe only 5. Okay. But today we're going to start off with 2 of the easier log laws. We're starting off with the product log law and the quotient log law, or if you're doing addition or subtraction. So the rule is if you have 2 logs with the same base, and those logs are being added together, you could combine them into one log where you multiply the arguments. So the addition of logs can be combined into one log that's being multiplied. Conversely, if you had 2 logs with the same base, log and a log with the same base, if they're being subtracted, you could combine them into one log that's being divided. So the arguments would become divided. Now whatever's being subtracted goes to the bottom.
So is it the same?
You can only do it if the base is the same.
Can we just do log number minus, or just divided by log number?
You don't even have to put log into that number. It just creates one thing. So if you had something like log 3 of x plus log 5 of x, you could not combine those because the bases are different. So that would not be a log law we could do. But if they had both been 3 or both been 5, then we could have multiplied the x's together to create one log. And we're going to do 3 practice problems, and you're going to do 3 practice problems. These log laws also work for natural logs. So we don't really need to write it out, but you could say that ln of mn equals ln of m plus ln of n. Right? Remember, lns are logs. It's just a base e. So of course the log law still applied then too. All right, how this looks in examples. We're going to do 6 together. We have 2 log statements. They have the same base. That means we could combine these logs because they're being added and it's the same base. 2 logs being added means you multiply the arguments. The arguments are 75 and 25. So this statement combined it becomes log base 3 of 75 times 25. We rewrote it as one singular log.
Do you have to write?
You don't have to. You can actually calculate it, which you should. So 75 times 25.
Oh wait, yes.
I'm trying to think of clever ways to calculate that, and I just couldn't do it. And then, because there's no letter in here, there's no variables, I could actually calculate that thing. So my calculator, I would go log 1875 divided by log 3. And I would get an answer of 6.86. It goes from. Remember, our calculators can't write bases. It's always base 10 in our calculator. So we convert that using change of base. Like these are the same things, and you use your calculator to calculate it. That's how it has to go in your calculator. Just because you don't get to choose the base in your calculator, it's automatically base 10. So it's just a rule that we learned yesterday. Alright, try another one. So we have 2 logs. They're being subtracted. What's important here is they have the same base of 2. They have the same base of 2. That means they can be combined into a singular log. So it becomes log still base 2 of 12 divided by 3. that would be log base 2 of 4. If you put that in your calculator, you go log of 4 divided by log of 2, and you get 2 additions. Which, if you remember what a log means, that makes sense. A log means what exponent on 2 would equal 4? Right? 2 squared would equal 4, so what exponent on 2 would equal 4? The answer is 2. Worst case scenario, just calculate it in your calculator. That's what I would do. Remember when you're putting in your calculator to close your bracket so you don't mess things up, it'd be log 4 bracket divided by log 2 bracket. And our last one we have here, we have log xz plus log xm minus log xn. People sometimes struggle with the order in which they need to do this stuff. So, if you have all these additions and subtractions, just work yourself left to right, and that'll make your life a lot easier. So I'm going to combine these two first. They would combine to be log x, z, n. And then minus log x, n. Still there. See how I combined the first two because they were being added, so I multiplied the arguments together. This thing can then be simplified to be log x, z, m divided by n. And that would be your simplified singular log answer. You're going to have to be able to combine logs into singular logs. The reason why you're going to have to be able to do that is you have to convert logs into exponents to solve some of these logs. You can only convert into exponential form if you have a singular log. Okay, so that's going to be the trick here, is combining. There's three more questions there. Let's try all three of them. We were converting those logs. The first one was an addition. So I multiplied the arguments together, so I went 100 times 0.25. And if I actually put that in my calculator, I get log 4 divided by log 5. The answer is 0.8. The next one, I have a ln and a ln. That means they're both base e. So if they're both base e, I can combine them. You take the first argument, you divide it by the second argument, so it would be a plus b divided by a minus b. You can't simplify those things at all. So you're just stuck with a plus b divided by a minus b. I have some confused faces on that next one, on the first one.
How is 100 times?
Yeah, that's for sure right. Yeah, it definitely is 25. Thanks for that. And the answer should be 2. Much better? Good. Less confused faces? Excellent. Okay. The third one. The third one is a little bit longer of a string. So I do the first two together. The first two are subtracted. So I was log 2x minus log 2x. So I divided the arguments, combined them into 1. Then I had log 2 of x plus log 2 of 4. So I multiply the arguments. Remember when you're multiplying, you just multiply the numerator straight across. So the 6 and the 4 multiply. And then you can multiply the denominator straight across. The denominators in this case are x, and then there's a divide by 1. But that's why the x doesn't change. It just stays as x on the bottom. So all you have to do is multiply the numerators across the top. 6 times 4 was 24. So then we had log 2, 24 divided by x. And then Sarah asked, like, how should you ever have to solve that? Like, why would this be beneficial to us? It's a good question. So if we had this question and then we said it was equal to 10, that means we could combine these into a singular log and say equals 10. So if I gave you this question, I wouldn't want just a singular log. I'd want you to tell me what x equals. So if you're looking for part of the log, what form do you have to be in instead? You're looking for something in the log, like your variable is part of the logarithmic equation. What form do you have to be in to be able to solve that? Exponential form. So I would have to change this to become 2 to the power of 10 equals 24 over x. And then I would have to change that around. So I would cross multiply. So x equals 24 divided by 2 to the power of 10. I added the 10 in to show you how this could happen. So then in my calculator I go 24 divided by 2 to the power of 10. And x would equal 0.23. That's how this stuff can become useful. So if I had asked you to solve for x, you would have had to combine it into a singular log so that you could change it to exponential form so that you could solve for x. And we will do some of that tomorrow, so don't worry about that. We're going to learn 3 more log laws tomorrow. And we're going to solve some of these things using log laws. After tomorrow, you'll have a 3-day weekend. You'll come back from the 3-day weekend. You'll have a quiz on everything we've learned in the logs unit. So we'll have converting into logs, converting into exponential, using natural logs, and we'll also have the 2 basic log laws, and then the 3 more complex log laws tomorrow. To be honest, 2 of the log laws tomorrow are really easy, and then 1 of them is important. Okay. All right, the rest of this